Kinetic and Gravitational Potential Energy. In this lesson, we're covering kinetic energy, the work energy theorem, gravitational potential energy, energy conservation, some applications, mechanical energy, and then we're going to do some practice. Kinetic energy, otherwise written as EK or KE. Kinetic energy is the energy of motion. When we do work on an object, energy is transferred into the system. Think of a person pushing a box. The person does work to the box, causing the box to move. As the person does work on the box gains EK as it starts to move. A train's engine does work on the train, causing it to move. A car's engine does work on the car, causing it to move, and so on. Kinetic energy. Kinetic energy can be found using the formula EK equals 1/2 mv squared. EK is the kinetic energy of an object in joules, m is the mass of the object in kilograms, v is the velocity in meters per second, and keep in mind that EK is a scalar quantity, so there's no direction. Check your understanding. Find the kinetic energy of a 48-gram dart traveling at a speed of 3.4 meters per second. So let's write down what we have. So we have the mass, 48 grams, which is equal to 0.048 kilograms. And we have the velocity of 3.4 meters per second. And we're looking for the EK. Now we know that EK equals 1/2 mv squared. So 1/2 0.048 times 3.4 squared. And that equals to 0.2774 joules. Now we need to have two sig digs, so our answer comes out to be 0.28 joules. Check your understanding. A 97-gram cup falls from the kitchen shelf and shatters on the ceramic tile. Assume the maximum kinetic energy obtained by the cup is 2.6 joules and that the air resistance is negligible. What is the cup's maximum speed? So V is our question. EK, we're told the maximum kinetic energy was 2.6 joules. That's going to mean just before the cup hits the ground, that's when it's hit its maximum speed, and that's when it's going to have its maximum kinetic energy. And the mass is equal to 97 grams, which is equal to 0.097 kilograms. EK equals 1/2 mv squared. EK is 2.6, 1/2, 0.097 times v squared. Now we're going to have to rearrange things. We're going to get 2.6 times 2, and we're going to divide both sides by 0.097, and we're going to take the square root of it to find v. And v comes out to be 7.32 meters per second. Now we need to have two sig digs, so our final answer comes out to be 7.3 meters per second. Now there's no direction because we're using energy, which is a scalar quantity. Work energy theorem. The total work done on an object equals the change in the object's kinetic energy, provided there's no change in any other form of energy. So for example, gravitational potential energy. We can summarize the relationship involving the total work and the kinetic energy as follows. So total work is going to equal to this one right here, which is going to be EKF minus EKI. Now if we break each one down, EKF is 1/2 mvf squared, and VI is 1/2 mvi squared. And in general, total work is going to equal to the change in EK. So for instance, if we go from having 3 joules of energy as our EKI to 6 joules of energy as our EKF, then the work that must have been done to the system would have been 6 minus 3, or 3 joules. Now an example of this happening is that let's just say a person is standing beside a box that is already moving at a certain speed. We'll call this V1. That person then does some work on the box by pushing it, causing it to go faster, giving it a V2. So now EKI was not equal to 0, it was already moving, and EKF, we can say, is bigger than EKI because work was done onto the system. Check your understanding. What total work in megajoules is required to cause a cargo plane of mass 4.55 times 10 to the 5 kilograms to increase its speed in level flight from 105 meters per second to 185 meters per second? So work is the question. The mass of the plane is 4.55 times 10 to the 5 kilograms. VI is 105 meters per second, and VF is 185 meters per second. Now our work energy theorem is going to say that work is going to equal to the change in EK, which is going to equal to EKF minus EKI, which is going to equal to 1/2 mvf squared minus 1/2 mvi squared. Now we put some numbers in, we get 1/2 4.55 times 10 to the 5 times 185 squared minus 1/2 4.55 times 10 to the 5 times 105 squared. And that equals to 5,278,000,000. Now we need to have that in megajoules. and that means we're going to divide by 10 to the 6. So essentially we're going to be dividing by 1 million, and that gives us an answer of 5278 megajoules. We need our answer to 3 sig digs, so our final answer is going to be 5.28 times 10 to the 3 megajoules. So we need 5.28 times 10 to the 3 megajoules to increase the plane speed from 105 meters per second to 185 meters per second. A fire truck of mass 1.6 times 10 to the 4 kilograms traveling at some initial speed has negative 2.9 megajoules of work done on it, causing its speed to become 11 meters per second. Determine the initial speed of the fire truck. Now, before we tackle this question, let's think about what this negative 2.9 megajoules of work means. When we have negative work done on something, remember, that means that if the motion is that way, the work done must be in this direction. Now, what kind of thing does that kind of work on motion in the opposite direction? Well, that's probably going to be the brakes. So the brakes are going to take energy away from the system, causing the motion to slow down. So we know that the VI is going to be bigger than the VF. Now we need to keep this in mind as we go through our question, make sure that our answer follows suit. So let's write down our knowns. We know our mass is 1.6 times 10 to the 4 kilograms. We know that the work is negative 2.9 megajoules, which is going to equal to, we're going to move our decimal over to the right 6 times. So 1, 2, 3, 4, 5, 6. Fill in our zeros, and we're left with negative 2900000. We know VF is 11 meters per second, and VI is the question. So let's write out our formula. We know that work is going to equal to the change in EK, which is going to equal to EKF minus EKI, which is 1/2 mVF squared minus 1/2 mVI squared. 1/2, our mass is 1.6 times 10 to the 4. VF we know is 11 squared minus 1/2 1.6 times 10 to the 4 times our unknown VI squared. And of course we know work is negative 2900000. So now we can solve for VI. Now let's give ourselves a little bit more room. So now how do we solve this? Well, it's not that difficult, but we just need to do a lot of rearranging. Now there's a few things you can do. You could bring this to that side of the equation and this guy to that side of the equation. That's probably going to make things a little bit simpler. So let's try that. So we're going to have positive now 1/2 1.6 times 10 to the 4 times VI squared equals 1/2 1.6 times 10 to the 4. That's this guy here times 11 squared, right? That's that right side of the equation. Now it's going to be plus 2900. Okay, now it makes it a little bit easier to do our work. On the left side, this 1/2 times 1.6 times 10 to the 4 equals 8,000. So it's just simplified. VI squared equals 968,000. That's this guy right here. Plus 2900. Now if we add these two guys together, we get 3868000. And on the left side, we have 8,000 VI squared. Now we're going to divide both sides of the equation by 8,000. And we get VI squared equaling to 483.5. Take the square root of both sides, and you get VI equal to 21.9886. We need 2 sig digs in our answer, so our VI is going to equal to 22 meters per second. Gravitational potential energy. So this is going to be EG, or PE, sometimes it's written as. Now this gravitational potential energy is the energy stored in an object due to its elevation above Earth's surface. And this could be any surface. It could be the surface of the floor. It could be above a desk. Whatever you're raising it above, that's what your gravitational potential energy is. And it's always the change in, because it's always relative to a certain area. So for this example here, we could have these boxes relative to the ground, to the floor, and that would have an EG. But then you could also say the EG for these boxes relative to the center of the Earth, which would be obviously much bigger. So it's always relative to something else. Now the potential energy at a height h above that point is equal to the work which was required to lift the object to that height. So for instance, if 100 joules of energy was needed to raise these boxes, the boxes now have 100 joules of potential energy. And you could experience that energy by dropping them. Say if you drop them on the ground, they'd make a loud noise. If you drop them on your foot, it would hurt a lot. Gravitational potential energy. So because gravity acts vertically, we're going to use h instead of d for the magnitude of the displacement. Remember our equation, work equals FD. Keep that in mind. The force applied to the box to raise it is in the same direction as the displacement and has a magnitude equal to mg. Therefore, the work done by the force is going to be W equals mgh. And we can see that in our formula up here, right? Our original formula, W equals FD. If we change F to mg and we change D to H, then we get our formula, work equals mgh. Now, since the energy obtained at the top is equal to the work it took to get it there, we can say that work is going to equal to change in EG, which is equal to our mgh. Things to keep in mind. EG is the change in potential energy from one height to another. So if we raise those boxes from here to here, we're going to get a change in potential energy. EG is the change in gravitational potential energy in joules, G is the magnitude of the gravitational potential energy in meters per second squared, and H is the vertical component of the displacement in meters. So make sure you have your proper units when you're doing your questions. Check your understanding. A diver of mass 57.8 kilograms climbs up the diving board ladder and then walks to the edge of the board. He then steps off the board and falls vertically from rest to the water 3 meters below. Determine the diver's gravitational potential energy at the edge of the diving board relative to the water. So if that's the diving board, and we have the water down here, then we're going to have a height here, and that height we're told is 3 meters. And we have our diver, I was going to draw him as a box, and he's 57.8 kilograms. So we need to determine the diver's gravitational potential energy, so EG, relative to the water. So EG is going to equal to mgh. M we're told is 57.8, G is 9.8, and the height is 3. And that equals to 1699.32. We need 3 sig digs, so our final answer becomes 1.70 times 10 to the 3 joules. In the sport of pole vaulting, the jumper's center of mass must clear the pole. Assume that a 59 kilogram jumper must raise the center of his mass 1.1 meters off the ground to 4.6 meters off the ground. So keep in mind this is what we mean. So there's the jumper. Center of mass is going to be right there. When they jump, their center of mass is going to be higher. So it's going to look more like this. So what we need, this height right here is 4.6 meters. This height here is 1.1 meters. So what's the difference in height? Well, that's going to be 4.6 minus 1.1, which is going to equal to 3.5 meters. What is the jumper's gravitational potential energy at the top of the bar relative to where the jumper started to jump? So EG equals question, which equals to mgh. M we're told is 59, G is 9.8, and the change in H is 3.5. And that gives us an answer of 2023.7 joules. We need 2 sig digs in our answer, so it becomes 2.0 times 10 to the 3 joules. A 485-gram book is resting on a desk 62 centimeters high. So let's write that out. So the mass is 0.485 kilograms, and the height is 0.62 meters. Calculate the book's gravitational potential energy relative to the desktop and the floor. So for A, it's a little bit of a trick. In this case, the height is 0 because it's resting on the desk. So relative to the desktop, the EG is 0. Relative to the floor, it's going to equal to mgh, which is 0.485 times 9.8 times 0.62. That equals to 2.94686 joules. We need 2 sig digs in our answer, so we're going to get 2.9 joules. The elevation at the base of a ski hill is 350 meters above sea level. So I'm just going to draw the ski hill here, and we're going to say that at this point, we're still 350 meters above sea level. A ski lift raises the skier, total mass 72 kilograms, so mass 72 kilograms, to the top of the hill. If the skier's gravitational potential energy relative to the base of the hill is now, so e.g., 9.2 times 10 to the 5 joules, what is the elevation at the top of the hill relative to sea level? So what we're going to actually figure out when we do this calculation is this right here. All right, that'll be what we find. And then we're going to take that and we're going to add it to our 350 to find our answer. So let's figure that out. So EG equals mgh. EG we're told is 9.2 times 10 to the 5 equals 72. 9.8 times height. When we rearrange and solve for h, we get 1,303.85 meters. So our total height is then going to be 1,303.85 plus 350, which equals to 1,653.8 0.9 meters, and we need 2 sig digs in our answer, so our final answer is going to be 1.7 times 10 to the 3 meters. One of the main ideas about energy is that it cannot be created or destroyed. It can only be converted from one form to another. In the example we have here on the bottom, we're going to see that as we lose EK, we're going to gain EG as our cart ascends our hill. So the size of the EG and the EK is represented by the size of the letters. So you can see at the bottom of the hill at this dip here, we have a large EK and we have a small EG. As we go up the hill, that EK is converted to EG, and we can see that represented by a smaller EK and a larger EG value. As it descends the hill, again, that EG is converted into EK, and our EG gets really, really small. When it gets on the ground, that EG will actually hit 0, and it will be completely EK at that point. And this is how roller coasters work. Essentially, they pull you up to the top of the hill using that pulley system. That gives the cart energy. It gives it potential energy. And then as soon as it lets go of that cart, the cart's able to just go down the hill completely under the influence of gravity. As it goes down the hill, it gets faster and faster and faster. And then when it goes back up to go on a loop or to go on a turn or whatever, that EK is converted into EG, as it's going to store some of that energy as potential energy. Now, some of this energy is lost, of course, in things like friction and air resistance. But for most of our problems, we're just going to assume that nothing is lost and that everything is converted from one form to the other. Some other applications include things like dams. So hydroelectric plants convert the EG of the water at higher elevations into EK as the water rushes down via gravity. So this is a picture taken at Hoover Dam, and you can see a whole bunch of water stored up here in the top. And this water gets up to the top via the sun. The sun is going to heat the water here, which then gives it energy, makes it go up into the air, and that's going to fall back down as rain into this top part here. And then we're going to store all this, kind of like a battery stores energy, and when we want to release it, we're going to let that water flow through what's called penstocks, which are located inside this dam here. It's going to flow through here, and as it does, it's going to spin a turbine. Think of a turbine kind of like a fan. So you have like a fan wheel like this, right? As the water passes it, it's going to cause the fan to turn. As the fan turns, it's going to cause these guys down here, these generators, to produce electricity. So we're going to have energy in the form of kinetic energy, generally of the water down here. That's going to be converted into thermal energy as we raise the temperature and cause it to go up into the air. And then it's going to fall back down, and then it's going to be stored as gravitational energy up here. And then again, that gravitational energy is going to be converted to EK as it flows down the penstock and gains speed. Mechanical energy. Mechanical energy is composed of both gravitational, so EG, and kinetic energy. So you can say that mechanical energy is going to equal to the total EG plus the total EK. Check your understanding. A 0.5 kilogram ball is traveling at 10 meters per second and is 2 meters above the ground. What is the ball's EK, EG, and total mechanical energy? Well, we know the mass is 0.5 kilograms. We know the speed is 10 meters per second. And we know the height is 2 meters. So for A, we're going to say that EK is equal to 1/2 mv squared, which is going to equal to 1/2 0.5 times 10 squared, which is equal to 25 joules. For B, we're looking for EG. EG is going to equal to mgh, which is equal to 0.5 times 9.8 times 2, which is equal to 9.8 joules. And then for C, we're going to be looking at the mechanical energy, which is going to equal to the EK plus the EG, which is 25 plus 9.8, which equals to 34.8. Now we need 2 sig digs in each answer, so A and B are good, and C needs to be changed to 35 joules. In summary, our kinetic energy, EK, is the energy of motion. EG, otherwise known as the gravitational potential energy, is the energy stored in an object due to its elevation above a reference point. Energy can be converted from one form to the other, for instance, EK to EG, and mechanical energy is the sum of the potential energy and the kinetic energy. Now to finish things off, what I'd like you to do is watch this video and then write down what is wrong, speaking energy-wise, because there's lots of things wrong with this video, but speaking of energy, what is wrong with this scene?